All right, we are in chapter 10 now, and we are in simplifying radical expressions. First one. Notice we're on 10.2a here. We're not going to be in 10.1. 10.1 is like graphing these radical expressions, and we've done a lot of graphing, so we're going to kind of skip through that and go right to 10.2. However, we do have three sections in 10.2. We broke it up into A, B, and C. So here, 10.2a. Let's get rolling here. What we're going to do is we're going to simplify radical expressions now, and we're just going to do some review. We should understand now that the first one here, the square root of 25, we know is 5. The square root of 121, this is one that's not a lot of people know, but it's 11. And even further, do you know what the square root of 196 is? Comes out to 14. So I'm just kind of reviewing, taking square roots and punching them in your calculator, things like that. Let's talk about the square root and what each thing is and how we refer to them. A radical expression is an expression that contains a square root. So over here to the right, this 5 times the square root of 6a is a radical expression. The radical part, that's the square root sign. So we call this the radical. Okay, and then the radicand is the expression that's underneath the radical. So our radicand would be this number 6a there. And then finally, the index. The index is the root being taken. A root being taken. And a lot of times we call that it's understood that it's 2. We don't have to put it in there, but in this case, the square root index is 2 because it's the square root. And this number out in front, just like it has in every other sense this year, it's called the coefficient. Number out in front of the radical. Okay, so those some terminology dealing with radical expressions. Okay, now let's talk about simplifying radicals. And so when we do this, we're not going to be able to use a calculator. And this is one thing we're going to kind of take it away from you, trying to make sure that we get this down when we simplify radicals. So we're going to have, when we simplify them, there are no perfect square factors of the radicand. Okay, so this is what we call it. If there's no factors, no perfect square factors, factors means we can multiply by perfect squares. So what we're going to end up doing with the radicand is we're going to break it down. Break it down. We're going to take that number inside the square root, the radicand, and we're going to break that down. We'll show you how to do that. And then we don't want to have radicands to have any fractions. That's not allowed. And then there are no radicals in the denominator of a fraction. So you can't have a square root sign in the denominator of a fraction there. Okay? So those are some three different rules to follow when we simplify radicals. The biggest thing, we're going to try to break it down, that first step. Okay? So let's look at properties of square roots and then how we go about breaking those down. So we understand there's a couple different things that we can do here, and that's if we have the square root of a times b, the radicand, ab, then we can separate that into square root of a times square root of b. That is allowed. Okay? So when we do that, like for an example, instead of using letters, let's use numbers over here. If we have the square root of 50, we can break that down into two different terms of that multiply to make 50. So let's put this second bullet point up first. So to simplify, we're going to find factors that are perfect squares and break it down. So that's the easiest way to do that. So we're going to take this 50 and we're going to separate it into two numbers underneath the radical that are that multiply to make 50. But we want one of them to be a perfect square. So if we go, say, square root of 25 times the square root of 2, that's just like we did over here. Okay, we're using letters. We can easily break this down because we know that one of them is a perfect square. This square root of 25 would become 5, and then we'd have the square root of 2 left over. We can't break that down. We don't want to have any decimal answers. So our answers are not going to be in decimal form. That's why we don't want to use a calculator to get decimal form. This is what we want our final answer to be. A perfect square, and then whatever you have left under the radical is not perfect, cannot be broken down. So 5 times the square root of 2 would be our answer to break down the square root of 50. We want to find a list of perfect squares in order to do that. So again, I'm just going to kind of put this up here, that we want to find factors that are perfect squares and break it down. So in this case, our example above, we found that 25 was a perfect square. There's a bunch of different ways to multiply to get to 50. You know, we could go 10 times 5, but neither of those are perfect squares, so that's no good. And then really 25 times 2 is the way to go, because 25 is a perfect square. Okay? So we try to do that and find perfect squares and then break it down that way. To help you with that, we're going to try and see what we can do as far as a list of perfect squares here. So this will help you as, you know, if you're unsure of what different ones are, this will help you. So we know that 1 squared is 1. And then, you know, because the square root of 1 equals 1. The next one, 2 squared, is 4. And the reason for that is because we know that the square root of 4 would equal 2 if we work backwards that way. And then we get 9 here because we know that the square root of 9 would be equal to 3 as we work backwards. And we can go on and so forth with 16 and 25. Now I want you to fill those out all the way down to 15 would be good. And that'll help you as we go through these problems, because we're going to want to do something with these. When you're working through these problems, you're going to have to check to see if these are numbers of factors. So when you're breaking down when you're breaking down a number underneath the radical, we want to check and see if these numbers in this column here are factors. Like in our above example, 50. Do we have any of these numbers that's a factor of 50? Yeah, 25 was, so that way we can use it as a perfect square. Okay, let's do some more examples here then. Let's start with the first one here, square root of 12. It says simplify and your answers may have a radical. No, we're going to change that. Your answers will have a radical. So remember, we're not going to use calculators here. We're not going to, I mean, you can use calculators to get a perfect square, I guess, but on the quiz and stuff, we're not going to let you use a calculator. You should be able to know those and go from there. So let's look at the first one. We're looking at the square root of 12. So we're looking for something that has a factor, a perfect square factor. So any of those numbers on that chart below or before this, do we have any of those that are a factor of 12 that would multiply to make 12? Sure. How about 4? So if we go ahead and go square root of 4 times the square root of 3, remember we can do that because 4 times 3 is 12. And then we know that this first one, square root of 4 is a perfect square. So the square root of 4 is 2. And then there's nothing else we can do with that square root of 3. So that would be our answer there, 2 times the square root of 3. Okay, let's go down to C here, C. Okay, and remember there's more than one way to multiply to get certain numbers, but we want to choose one with the perfect square. And if there's more than one perfect square, then you want to choose the greatest one because you'd have to break things down even further. So 90, if you look at that chart, are there any factors in there that are perfect squares? Well, 9 is a perfect square. So if I went ahead and said, all right, let's go square root of 9 times the square root of 10. And this is just our square root product property where we can multiply numbers to make that. So now I also know that we can say that the square root of 9, that's a perfect square, 3, and then we would have the square root of 10, and there's nothing else that we can do to break that down, so that would be our answer there. Okay, and let's try one more here, and going to F. And just a reminder that there are no decimals allowed. No decimals allowed. Notice my answers in the previous two. We don't have a decimal. We have radicals. We broke it down to a perfect square times a radical of something that cannot be broken down any further. All right, so 45. Again, I'm going to use 9 because 9 is a factor of 45. So I'm going to go square root of 9 times the square root of 5. And then we're going to break that down because we know we got a perfect square here, which is 3. Square root of 9 is 3, and it would be times the square root of 5. And that's how we break those down. Okay? You can try the other ones on your own, but that's kind of the way we would simplify these things. Okay? Let's talk about variables now. You can also take the square root of variables, and we've done this kind of before a little bit. Maybe you didn't even know you were doing it, but you know that the variable is a perfect square when the exponent is even. So if it's even, it's always going to be a perfect square if you remember your exponent properties, because when you multiply exponents, you add their exponents. So in this case, you know if the exponent's an even number, that it's a perfect square. So for instance, if we went ahead and said, let's use an example of, say, the square root of x to the fourth. Because that exponent is even, it's 4, then I know that we can go ahead and break that down as a perfect square. So to find the square root of a variable, what we're going to do is we're going to break up the variable into groups and square root each piece of it. Okay, so when we break this into groups, basically we would say, if we did that, this thing would break down to square root of x squared times the square root of x squared if we just did that like we did with the numbers, but now we're using a variable. And then we know that, hey, the square root of x squared is going to be x, and then the square root of x squared here is going to be x. So we'd have x times x is x squared. Okay? And I know we did that, but if you just wanted to go from this one up here straight down to here, you could, because we know it's a perfect square, we would just have to divide that exponent by 2, and because it's even, and it would be x squared. So you could do that. You could jump right to there, but I'm just showing you how they got that reason, how they got x squared from there. But it is a perfect square, and basically you just take that exponent divided by 2. Okay? So that is how we take it, a variable. So let's do a few more examples here with involving variables. So we already did letter A. We just did that example on the last page. So let's look at C here. And the tricky thing is, what if we have a variable with an exponent that's not even, like an odd one? So we'll do a couple of those examples here. Okay? So when we look at this one, we're going to break these apart. We've got square root of a squared b to the fifth. So we could break this apart and say, all right, well, let's take them separately. Square root of a squared, and then we'll say we'll multiply by the square root of b to the fifth. And we'll take care of that b to the fifth in a second, because we know the square root of a squared. We do know that those two undo each other, right? Square root of a square would undo each other. We just have a. And then over here, we've got this b to the fifth. Well, can we do something to get it to a perfect square? So a little tip is to say, hey, just subtract 1 and multiply it by b to the first. From whatever the variable is, subtract 1. So we could break this down, say, to b to the fourth times the square root of b to the first. Because remember, when we multiply exponents or variables with the same exponent, we add them. So this is basically b to the fifth, b to the fourth times b to the first. But what we did by just subtracting it by 1, we made it an even number, so we know we have the perfect square. So we can take this b to the fourth and make it b squared, because that's a perfect square. And then we've got the square root of b over here. There's not much else we can do there, and so we would just kind of keep it as the square root of b. Can't break that down anymore. But don't forget about your a over here, so we're going to bring that over here, and this would be your final answer. A b squared times the square root of b. I know it looks funky because there's a b on the outside and a b on the inside, but we can't do anything with that square root. So that would be your final answer to that one. Let's look at D. Both odd numbers now. So we have to take D to the 11th, square root of D to the 11th, and we're going to separate that. We're going to bring the E to the 13th over here. So let's work with that D to the 11th first. Okay? So the first thing we're going to do is we're going to break that up. And again, my little trick is just drop that 11 down by 1 and break it down that way. So D to the 10th times the square root of D to the first. And by doing that, we're able to say, okay, now we at least have one perfect square with just D to the 10th. So when we do that, we're going to go ahead and get rid of that and make it D to the 5th because it's a perfect square. And then D to the first, there's not much we can do. So I'm going to write that over here. It's just going to be the square root of d, keeping it over there. Okay? E to the 13th power. E to the 13th. So the same thing I'm going to do. I'm going to drop this 13 down by 1 and make it e to the 12th times e to the 1st, both under radicals. Square root of e to the 12th times the square root of e to the 1st power. Okay? And e to the 12th, we know is a perfect square because it's an even number, so we can divide that by 2 and make it e to the 6th outside the radical there. And there's a reason I put it over here, because we want to keep our numbers outside the radical on the left and then the numbers inside on the right. And then we know the square root of e to the 1st, we just have to keep it as square root of e. So I can put that underneath the same radical for the same property reason. I can put those both underneath the same radical symbol. So that would be my final answer here. And when we write that, we want to keep the numbers that we've already broken down that were perfect squares that don't have a radical on the left-hand side as our coefficients, d to the 5th and e to the 6th. And then the radicals are the last things in there, the square root of d times the square root of e. Okay. Let's do a couple now where we put it together where we have numbers and variables underneath the radical. Okay, so let's look at letter B here. Letter B. So I've got 81a to the a cubed, right? So let's break this up, and I'm going to break up the numbers and the variables. So when I do this, I'm going to say square root of 81 times the square root of a cubed. Well, right off the bat, I know that our square root of 81 is a perfect square of 9, so I can put that down there. And then I'm going to break this down into the square root of a squared, because it's an odd number, times the square root of a to the 1st. And then again, I also know that the square root of a squared is a, and then there's nothing I can do with the a to the 1st here, square root of a, so I would just keep that underneath the radical. So my answer would be 9 times a times the square root of a. And I know some of these look funky, but this is the way that we break these down. Notice there's no decimal answers. Now, we look at 72. Okay? Our number letter C here. Letter C. 72, d to the 8th. Now, there's more than one way to get to 72, and there's more perfect squares. So you would have to kind of choose. My advice is to use the one that's the greatest number, because I know a lot of you guys are going to say, oh, 9 times 8 is 72 right off the bat. So let's go ahead and break these down to go square root of 72, and then we'd have the square root of d to the 8th over here. Okay? Well, if we did that, let's go ahead and use 9 and 8 in case you ended up doing that. So we would have the square root of 9, because that's a perfect square, times the square root of 8. And we do know also that the square root of 9 is a perfect square, so it would be 3. And then we'd be, we still have to do some work with that square root of 8 here, because now we know, okay, this is the square root of 4 times the square root of 2. And then we have a perfect square here that makes 2. And we still have that square root of 2 that we can't do anything with. We drop down there. Now let's take care of the d over here. We know that this would be a perfect square because it's an even number. It would be d to the 4th. So I can squeeze that d to the 4th right down in here. The only thing is I would have to do is I'd have to kind of multiply this 3 and the 2 to make 6. D to the 4th times the square root of 2. Okay? Now that's if you use 9 times 8. But like I said, if there's two perfect squares that go into a number like in 72, use the greater one because it would probably be less work for you. So if you look at the square root of 72 again, let's say I did the square root of 36 times the square root of 2 instead. Well, I know the square root of 36 is 6, and then I've got the square root of 2 here, so that makes it a lot faster. And then my d, I could add my d to the 4th in there, make it a little bit faster. So if you have two numbers that are perfect squares that go into something, I would use the greater number. Okay? All right, so let's roll on here. We'll go to the lesson summary now. So I want you to explain in your own words how to simplify a radical, and then that would be your lesson summary. You've got to do these guys, and then our practice problem here is to simplify this one, square root of 18x squared. Okay? So that's it for 10.2a. The rest of the notes here for the rest of this chapter are a lot shorter than this one. So bring some questions. I know it's tricky at first, but I think you'll get the hang of it. Okay? We'll see you later.